Okay, back to Laplace transform. Can you go down to the pad, please? Great. So Laplace transform. Ignoring all the horrible details that I went over last time, probably in too much detail, the Laplace transform is just defined by this, and this is something you'll use many times, not just in this class, but at least 4 or 5 others. And so you just need to know that this is the Laplace transform. So what I didn't mention last time is you might ask, why should we need to know the Laplace transform? And I haven't yet told you, but it'll become clear. Within 2 weeks, it'll be very clear why you need to know about it. So this is the definition. It takes a time signal, and you simply plug it into this integral, evaluate this integral, if possible, and you get a different complex number depending on what the complex number s is. And the function that maps s into whatever this thing evaluates out to, that's the Laplace transform. And the tradition is that that's given by a capital F. So last time we looked at a number of examples. For example, either a constant or a unit step. They give the same thing. It's the integral of 1 e to the minus st dt, and that turns out to be 1 over s. And I think I said more than enough last time on details like when does this integral exist and all that. Not one of those details will ever matter to us. So, but I figure, just to be honest, I'll bring them up once. As another example, let's look at a sinusoid, like for example cosine omega t. If you take cosine omega t, your best bet is actually to split it up into 2 exponentials. So for example, here you write cosine as 1/2 e to the j omega t plus 1/2 e to the minus j omega t, which I'm sure you remember from 101. Doing that, now we take the integral of this, and that splits up. I can put the half outside, and then I integrate this. If I integrate this, I'm going to get 1 over s minus j omega, 1 over s plus j omega. And when all the smoke clears, I have s. I put these on a common denominator, so I get s minus quantity j omega squared, which is s squared plus omega squared, and I get this expression here. Okay, so s over s squared plus omega squared. And this formula, for example, is valid for whenever the real part of s is positive, the integral makes sense. But this formula actually makes sense for all s except for 2 complex numbers, which are plus and minus j omega. Okay? Because when I plug in s and plus or minus j omega, I get 0 in the denominator here. Okay, so one issue that we will have to deal with, and there's actually a subtlety here, and that is the issue of impulses at t equals 0. So it turns out in a bunch of cases, we're going to deal with some signals that have impulses at t equals 0. For example, just a unit impulse. What we do in the Laplace transform then is actually, in fact, you have now 2 choices, and only 2. And the key is to be consistent. You either include all the impulses at t equals 0, or you don't. And in fact, you will find books that take either route, right? So some books will just exclude. They'll make this 0 plus, thereby ignoring any sort of impulse action that happens at t equals 0. But in fact, probably the most useful is 0 minus. This allows you to, what this does is it takes into account any impulse that occurs at t equals 0. So that's how that works. That's what we're going to do. Now the problem is, it means you have to kind of be on your toes. You can't mix and match these things and decide all the formulas. We have to be very careful about this. You have to be very careful about what happens when you have an impulse at the 0. Do you sort of include what happens at 0 or not? And our convention is that we will. I think this is the dominant one, but I do know that there are some books where the convention is 0 plus. The implication, of course, is that you could someday open a book and find a formula slightly different from one you see in this course or the text, and just don't be shocked by it. It is more than likely related to this fact. Okay, let's do a simple example. A single impulse. So an impulse at t equals 0. Now the Laplace transform is the integral from 0 to infinity of delta of t e to the minus st dt. Here it's important for us to use our convention, which is that it's 0 minus, meaning that we're going to include this delta function, right? If I put a 0 there, here, this is one of those awful ambiguous things, right? I have an impulse and my range of integration is right from where the impulse is to the right. So this is one of those things where basically nobody's parser should let this go by. Everyone should, at a minimum, you have to look at this and say, what exactly do you mean here? So you should come back. With the 0 minus, it makes it completely unambiguous. The intention is that we will include this impulse. Now, if you do this, of course, this simply picks out the value of this function at t equals 0. But the value of e to the minus st when t equals 0 is 1. And it's completely independent of s. So the Laplace transform of the delta function is simply the constant function 1. Okay? So that's how that works. Now, as another example, you can take the Laplace transform of a delta function differentiated k times. Well, what you get is minus 1 to the k times the kth derivative of e to the minus st with respect to t, differentiate, and then evaluate it at t equals 0. And you will simply get s to the k. So the Laplace transform of a doublet, for example, that's delta prime, is precisely s. Okay? So these are the Laplace transforms of delta functions and their derivatives. Okay, important property is linearity. We've already used it a couple of times, but without making a big deal about it. And what it says is this. It says that if I take a Laplace function, a signal, f, that's a signal, I multiply by a scalar, that's another signal. AF is a signal. I then apply a Laplace transform to that, and what I get is a function of a complex frequency variable. What I'm telling you each time when I move my fingers here is I'm telling you what the data structure is of the expression between my fingers. Okay, so that's now a Laplace transform, which is a data structure which is a complex valued function of a complex variable. Okay, so that's equal to that, which is the Laplace transform of f times a. So it's very easy to read these things and sort of, I mean, it's only, I don't know, 8 ASCII characters. It says a lot, though. So, and it's not simple. So watch out. Okay, now similarly, if I take two signals, I can either sort of, in fact, I'll say this the way people would say this informally. Informally, what you would say is, oh, you can add signals either in the time domain or the frequency domain. So this would be the way people would conceptualize this fact. This says, I can take two time signals, I can add them together to get a new signal, a new time signal. I can take that signal and take the Laplace transform, and I get a complex valued function of a complex variable. Alternatively, I could take the Laplace transform of each signal separately, right, and then add these. So for example, this plus, we're overloading operators here. Okay, plus means something extremely different here and here. They're totally different. Same symbol, overloaded operator. Overloaded operator. What plus means here, this is the plus that adds two signals together. That's what this plus is. Okay? This plus is the plus that adds two complex valued functions of complex variables. Okay? So what you can do when I mention these things is you can either listen or you can ignore it on these types of things, right? Because the power of symbols like this, where you highly overload operators, the power is that when you see that, you know, it kind of looks like 1 plus 1. And so it suggests all sorts of things about 1 plus 1 and things you know about 1 plus 1 and 1 plus 2. That's also simultaneously the danger of overloading symbols, is that you can just casually look at f plus g and you say, yeah, so what? It's a very complicated thing. So I'll just mention these a couple of times and then I'll quit. So let's look at, I mean, as an example, if I asked you what's the Laplace transform of 3 times delta of t minus 2e to the t, well, we could plug it in, but in fact, we've already worked out the Laplace transforms of a couple of these parts. We know the Laplace transform of delta of t is 1. 3 times that, you get 3. And then the Laplace transform of e to the t is 1 over s minus 1. Okay? So minus 2 times e to the t has Laplace transform minus 2 over s minus 1. And when I get this, and I put this on a common denominator, and I get that. Okay? So this is sort of the idea. Now another important property is the one-to-one property, and here again there is a subtlety, which I'll say a little bit about, probably more than I should, but I'll say a little bit about it. roughly speaking, and I'll say what I mean by roughly speaking in a second. So the Laplace transform is 1-to-1. Now, that's actually that's sort of almost suggested by the language. When someone comes up to you and says transform, of course they're talking about a mapping or a function. But usually when you say transform, it suggests, at least, I guess, in informal speech, or informal mathematical speech, it suggests that you're merely transforming something. You're not losing any information. In other words, when someone says transform, you expect there to be an inverse transform, something that will sort of transform it back. So you transform something into some representation, and you should be able to transform it back. That's sort of the language is chosen to suggest that this is the case. And in fact, this is almost the case. And we'll talk about the exception. So it is almost true that the Laplace transform doesn't lose information. In other words, that you can take a Laplace transform, then you can take an inverse Laplace transform. Okay? And in fact, you could just go along thinking that you could just take an inverse. Well, we will, in fact, spend more than a week talking about inverse Laplace transforms. That's one of the skills and things you'll leave the class with, is an ability to work out an inverse Laplace transform. So let's just talk a little bit briefly about what it means. First, what it means is this. It says that if you have two functions, two time signals, and their Laplace transforms are the same, then they're the same. Now, in fact, it's not quite true, and we'll talk about what the exception is. Okay? By the way, this is not easy to show. This is not simple, and I will, you'll be spared a discussion of this. Okay? So, again, taking on this level of informality, you can say that the only function, f, whose Laplace transform is 3s minus 5 over s minus 1, that's what we just worked out on the page before, is in fact 3 delta of t minus 2 e to the t. In other words, the inverse Laplace transform of this is that. Okay, now I'll say what almost is, and I'm pretty sure this will never, ever bother us. Okay, the Laplace transform, the definition, and in fact, this, if you don't care about these things, that's fine, but I'll just say it to be fully honest. The Laplace transform, here's the definition. It depends on an integral. Okay? Now we do a thought experiment. Take a function f here, and what I want you to do is to find a new function g. And g of t is going to be f of t if t is not equal to, I don't care, 3. Okay? For t not equal to 3. Now for t equals 3, I'm going to make g have a new value. So what's, 7. There we go, minus 7. Okay? So let me sketch f and g. Here's f. I don't really care what f is. That's f. Okay? And here's f. Here's t equals 3. And g looks almost the same, except that at t equals 3, it has this value. Everybody understand what the two graphs are? So f is just a smooth curve, and g is a smooth curve, except at t equals 3, for some perverse reason, I simply make the function have a bump, right? A single value, and I make it minus 7. Why? I don't know. I just do it. Now, what's the integral of f e to the minus st compared to the integral of g e to the minus st? In fact, if you're integrating a function and you take its value at just one point and you change it, what do you do to the integral? What do you think? You don't do anything at all. You do nothing at all, right? If you take a function and you change it at a single point, you can do anything you like with a single point. Because a single point has no width and therefore no area and all that, the integral doesn't change. We should probably move on because I guess I'm seeing about, I don't know, 80, 90 like totally puzzled looks. Here's what I'm saying. Here's a function right here. It's 0 everywhere except at t equals 3, and I make it 4 there. Okay, so there's my function. Looks like this. What's the integral of that? It's 0, and there's no question about it. The integral of this is 0. Now, by the way, this is very important to keep straight. If this were a delta function, that's a totally different story. If this were some kind of impulse, right, then the integral would be, 1 if it was delta, if it was delta t minus 3, right? But if the function simply has the value 3 or 8 or 5 at a single point, its integral is 0, it's zip. Okay? So back to my example here. F and G, because they only differ at one point, they have exactly the same Laplace transform. Okay? Well, because now, suppose someone asks you to take the inverse Laplace transform. What happens? Well, you have no way of knowing whether or not the original function was either f or g. Got it? So what it says is, it says that the inverse Laplace transform, I mean, the way people act, I'll tell you the way it's said technically. The inverse, what you can reconstruct from the inverse Laplace transform is you can reconstruct the function almost everywhere. That sounds informal, but it's actually technical. And what it says is, you're going to get you can't be wrong and have like a lump in a function where there wasn't a lump somewhere else. But in terms of what you reconstruct at a given point, at any given point, is not an issue. And so this will come up in a couple of cases. For example, here will be define a function that looks like this. It's a rectangular pulse. When you work out the inverse Laplace transform and someone says, what's the value right here? It's going to turn out it's not particularly well defined. Either an integral won't converge, or you might get 0 when in fact the original function had a 1 here, or so on. So, okay, I think I've spent more than enough time on this. Yeah, I'm getting confirmation that that was more than enough time on it. Okay, so these things, like this issue of the region of convergence, this is almost always not going to bug us. However, every now and then I'm going to make a comment about this, and it's probably important to point out. Okay. Now, having brought up the inverse Laplace transform, I can just tell you what it is. As I said, whenever someone says transform, the hint or the idea is that you can invert or undo a transform. What you now know is that you can almost undo the Laplace transform. In other words, you don't expect to recover it and get every point exactly, but you're going to recover it, and maybe you'll be off at 1 or 2 points, and it won't matter. So the inverse Laplace transform, there's a formula that looks just like the Laplace transform. Okay? I will not even go into the details of what the formula means. I'll tell you why. Because it turns out this formula is almost useless in practice, shockingly. Okay? And the reason is you look at the formula and you say, all right, well, that's the inverse Laplace transform, so what? And it'll turn out that that's not the point of the inverse Laplace transform. That what will emerge in the next 2 or 3 weeks is the important point about the Laplace transform is to get a qualitative feel for what the signal is doing. For example, if I asked you, is f oscillating? Is it wiggling? Is it growing with time or decaying? And I say, well, I mean, the answer's right here. Take a look. Then everyone here just looks at that and says, I don't know what he's talking about, right? This doesn't give you, I mean, unless you're awfully good at carrying out integrations in the complex plane in your head, this formula gives you no insight, although it does undo the Laplace transform. So it's funny, I thought last year I didn't even mention it, and then all sorts of people got agitated and they said, hey, you were holding back on us. I found a one-line formula somewhere, and I was thinking, well, I was hoping no one was going to find it. And so there it is. So that's it. You'll never see it again. It's one of those very beautiful and totally useless results. Okay. So now what we'll do now is we're going to look at a whole bunch of other properties of the Laplace transform. And what I'm going to do is actually I'm going to skip a couple of them and kind of concentrate on the important ones. There's long lists of these things. And in fact, you'll probably end up knowing most of them anyway. The first is time scaling. So if I take a positive constant a and I scale time in my signal. So for example, if I make a big, then times are scaled by a. They're spread out, and frequencies are scaled by 1 over a, and that makes perfect sense, right? So the Laplace transform of g, which is this time-scaled version, is 1 over a times f of s over a. Now, I'll tell you what I do. It depends on how recently I've done all this stuff. If I've done it recently, I actually remember this formula. But usually, I just remember, when I see time scaling, that there is a formula, and then I just go derive it myself or find a book or whatever, depending on. Usually it's just easier to derive it yourself. Now, as an example, you can work out things like this. We knew the Laplace transform of e to the t is 1 over s minus 1. Therefore, the Laplace transform of e to the at is, that's a time-scaled version of that, is this. You just simply plug in the formula. Now, nothing has been saved here because it's extremely easy to just plug in the definition here and find the Laplace transform, but it's just an idea. And I won't go through the derivation. It's exactly 3 lines. You just plug stuff into the integral and you see what happens. Next property. This one is actually really important. This is, in fact, why you have the Laplace transform. It's this page. This is it. This is everything. Okay? And here it is. If I take the derivative of a signal, time derivative of a signal, and I take the Laplace transform, what I get is s times f of s minus f of 0 minus. Okay? Now, this is exactly like, or very, I should say not exactly, it is very much like phasors in sinusoidal steady state analysis in 101. In 101, if you had a phasor representing a sinusoid, and then you took the derivative of the sinusoid, the associated phasor is simply j omega times the original phasor, right? So that's sort of the idea. In other words, when you have a phasor transform, if you want to glorify it with that name, in the phasor transform, time domain differentiation becomes multiplication by j omega, multiplication by the frequency variable. Same thing happens here if you ignore this second term. It says that when you take the derivative of a signal in the frequency domain, that's the way people would express this kind of, in informal terms. It's in the Laplace transform domain, or in the frequency domain, people would say, you are multiplying by the frequency variable. That's what you're doing. Okay? That's the idea. Now, there's this other term here, and it's also really important. This term here gives you the effect of the initial condition. Okay? So that's going to become critical. So that's it. So roughly speaking, time domain, the Laplace transform turns differentiation into frequency domain multiplication. That's what it does, by s, by the frequency variable. So let's work out an example. You have e to the t. Its derivative is, of course, e to the t. The Laplace transform of f is the same as f prime is 1 over s minus 1. Let's try our formula. Well, according to that, the Laplace transform of f prime is s times capital F of s, that's this, minus f of 0 minus. Well, e to the t is, there's no bump at t equals 0 or something like that, so it's just 1 at t equals 0, or 0 minus. It doesn't matter. It's continuous at t equals 0. And so we get this. And if you multiply this out, you'll find out that that is, in fact, the same as that. As another example, we can work out what the Laplace transform of the sine is. So sine omega t, which is minus the derivative of cosine, and you work it out, and you get this. And of course, here, you could just as well have worked out the integral yourself. That's it. Okay, so this one is so important, as you'll see momentarily, that it's not bad to work out, to actually see how this formula is derived. In other words, it's going to be the basis of all sorts of stuff, and so it's not bad to see that it's not just not hard to derive. Here's g of s. That's the Laplace transform of the derivative. Now we're going to integrate by parts. So I'll make this. That's my dv, and that's my u. So I get, this is it. The integral of u dv is uv minus integral v du. And when I plug that in, I get uv, here's uv, evaluated from infinity to 0, minus integral v du. And I work this out, and it's just all just pops right out. Okay? And you get this. That's exactly, so there it is. In other words, it's just integration by parts. Okay? Now, along with derivatives, higher order derivatives, if you apply this recursively, here's what happens. Laplace transform of the second derivative is, of course, s times the Laplace transform of f prime minus f prime of 0, and you work it out. And you get s squared f of s minus s f of 0 minus f prime of 0. So that's the idea. And you have similar formulas for an arbitrary derivative. Okay. Now we're going to do a simple example, which you know the solution to already, but you will see now exactly why this is a very, very big deal. Right? I mean, technically speaking, if you're really on your toes here and keeping track of things, I came last time, I said, here's the Laplace transform, here's a bunch of properties of it. I talked a bunch of philosophical nonsense about, points being varied and inverse, none of which made any sense, and region of convergence. But if you're really on your toes, you realize that so far I have not told you one useful thing you can do with the Laplace transform, all right? So we have to be honest about this, right? So far I've just told you a whole bunch of definitions and things like that. Now, of course, a lot of classes end that way. You've just learned you learn a lot of things, but they forgot to tell you what it's useful for, okay? So just to keep the record straight. Okay, so let's look now at, and this won't be an honest application because this is a problem you already know how to solve. So there's no reason to use the Laplace transform. But let's look at it anyway, and you'll get the idea. Here's an RC circuit. Okay? The input here is a unit step. Okay? It's 0 volts. It pops up to, the initial condition on y is 0. This pops up to 1. And you all know exactly what the solution looks like. Looks like that. It's 1 minus e to the t. Okay? That's the solution. You know this from 101. Now you also know that this is an extremely important practical circuit, as simple as it is. This circuit, for example, is a simplified model of what happens inside an integrated circuit. This is one gate driving another gate. They might be separated by 50 microns. Okay? This R represents a wire, an aluminum wire, deep inside, a thin aluminum wire deep inside an integrated circuit. This capacitance represents the capacitance of the MOS transistor, which is the next gate. Okay? By the way, what I'm saying now is all cultural enrichment, so if you don't get it, there's no harm done. And so, in fact, what this says is this. This shows what happens when one gate deep inside an integrated circuit switches from 0 to 1. The voltage at the other gate to which it's connected does not change instantly from 0 to 1. It might take 2-3 nanoseconds to change. Why is this important? It's extremely important because it is precisely this delay that determines how fast you can clock that chip. Okay? If it takes 2 nanoseconds before this signal is up here, then you can clock that chip at 450, 500 megahertz. Okay? If it takes 20 nanoseconds, you're going to have to clock it much, much slower. Okay? So I mentioned this, I guess Bass probably went on it, did he? About these things or not? He probably did, yeah. Okay, anyway. So, all right. Needless to say, 1 ohm and 1 farad are not the values found in integrated circuits. No. Okay. And the time scale, of course, there is in nanoseconds or even picoseconds or something like that. Okay, so that's it. You know the solution. Let's see what happens. In the second lecture, what we worked out was that this signal y, which is the voltage across the capacitor here, satisfies this differential equation. Y prime plus y equals u. Okay? Now, what we're going to do is we're going to take Laplace transforms of this differential equation. Now, we take the Laplace transform of u, that's just capital U, that's capital Y, and now y prime, that's derivative. That gets turned into sy of s minus y of 0. Y of 0 is 0, so it's sy of s. Now, look at this. This is it. This is the whole point right here. The whole point is that a differential equation just got turned into an algebraic equation. That's the entire point of the Laplace transform. It's right there. You know, this is exactly like phasors, right? That when you have a big old LC circuit, R's, LC's, all sorts of stuff, and it's in sinusoidal steady state, it's described by a huge, hairy set of integral and differential equations. Okay? Now, if you're really, really smart and can look at huge coupled sets of integral and differential equations and get a feel for what it does, good for you. Okay? But the point is, if you then use this phasor analysis, what was integration and differentiation now becomes multiplication. Now, it's complex, sure, and that takes a little bit of imagination to start imagining currents, voltages, and resistances, otherwise known as impedances, to be complex, but this is the idea. Same thing happened here. Differential equation just got turned into an algebraic one. You can just solve this for y. This is look, there's sy plus 1 times y, so I rewrite it as s plus 1 times y. And it's algebra. I just rearrange a few things. Oh, u is a unit step. The Laplace transform is 1 over s. It's just algebra, and all of a sudden I get y of s is 1 over s times s plus 1. Well, we're almost there, because at least we know that we now have computed the Laplace transform of the solution. That's pretty good. How do we get y? Well, I don't know, if I were nasty, I could say, well, we're all set. You just plug this in here and you get the solution. And actually, if you're pretty good at complex variable integration, this would actually be okay for you. Okay? But if you don't mind, I'm gonna find the inverse Laplace transform of this in the way that you will also be able to do it by next week. The way to do that is I'm simply going to write this expression as, I'm going to rewrite it into something which is exactly the same. It's 1 over s minus 1 over s plus 1, like that. You have to check that this is the same. You have to put these on a common denominator, and you put s plus 1 there, minus s, and you get 1, and everything works out. Okay? Now, you could ask me, first of all, why did I do this? And my answer is, none of your business for 2 weeks. You'll find out later. Okay? Or how did I know to do this? Because I know what the next 2 weeks of lectures are. That's why. You will too. Okay, so that's my answer to that question. And now, if I ask you, what's the inverse Laplace transform of that? We apply linearity, number 1, and the fact that we've seen them already. 1 over s is a unit step, or 1. 1 over s plus 1, we saw that. That's e to the minus t. Okay? And so the solution is now 1 minus e to the minus t. Okay? Of course, this is kind of dumb because you knew this in 101, right? Here's the difference. The difference is in 101, all you knew about was first order circuits. And, right? That's all that's covered there. The nice part is that the method that I just showed you here is going to work for giant circuits with zillions of capacitors and zillions of resistors and all that. Lots of inductors, all sorts of stuff. And so that's kind of the idea. Now, when you finish one of these things, in other words, what we've really done is we just solved a differential equation. That's what we really did, using Laplace transform. And when you finish that, you go through a bunch of steps, and what you always should do in the end is go back and make sure that what you think solves the differential equation actually solves it. And that's very easy to do. You just differentiate what you claim to be the solution as many times as needed, plug it into the differential equation, and either you'll get a tautology or you will not. Right? And either the left-hand side will equal the right or it won't. And if it does, great. And if it doesn't, go back to step 1 and recheck everything. So that's the idea. Okay. So this is really this is the whole point. Don't worry if you don't get it, because you will after we do this for 3 weeks. Okay. There's a question.
How do we know, like, when you take use the table to, like, for example, on page 312, you take the Laplace transform of f and f prime, and I guess you end up with the same number. So how would
that's only for this particular example. I mean, that's because e to the t, the derivative is e to the t. Yeah, this is not a general, this for sure is not a general fact. This is true only because f is e to the t, and f equals f prime. Okay, let's go back to integral. Well, let's see. If you let a signal be the running integral of another signal, so you integrate it from 0 to t, then it turns out the Laplace transform is 1 over s times f. Now this is also reminiscent of stuff you've seen from 101. Also, you should begin to make sense and patterns here. If differentiating is multiplying by s, right? What do you imagine integrating is? It's dividing by s. Okay? So patterns should start making sense. Now there's a little detail here. For example, you don't see the annoying term in front about f of 0 minus. Why is that? Integration and differentiation are inverses, so what's wrong? What's wrong with that little term there? The answer is really simple. The answer is that integration and differentiation are not inverses. That's a big lie. That's false. Okay? They're very close to inverses, right? They're not inverses because of the initial condition, right? If I take a signal and I integrate it and then I differentiate it, I recover the signal always, right? If I take a signal and I differentiate it and then I integrate it, I don't recover the signal. I recover the signal, but any constant part of that signal is now gone, okay? All right, so they're not quite inverses, and that's why the formula for the integral is not quite the inverse of the formula for the derivative. Not quite the same. And it's a basic fact from calculus that informally, integration and differentiation are inverse operations. But in fact, if you think carefully about it, they're not quite. Okay? I mean, simple example, you take a constant, you differentiate it, you get 0. You integrate 0, you get 0. Okay? It does not recover the constant, unless the constant's 0. Okay, so, and you can start relating this to various things. I will not work out the integration, the derivation of this. You can look at it yourself as to how that works. But it's just a question of sort of plugging stuff into the integral, changing a couple of variables, and so on, and you'll finally get this result, which is g of s is 1 over s times f of s. Okay, we'll look at. Let me see here. I think we're going to look at one or two more of these, and then I'm going to propose to. Then I'm going to probably quit. We'll look at another one. Time delay. So here, suppose you have a signal and a positive time t. Let's define a new signal as the original signal delayed capital T seconds. T is positive, okay? So here's a plot. Here's the original signal. And the new signal is the old signal delayed. Now, actually, you have to, in fact, I still can't get it straight. When a plot shifts to the right on the time axis, in fact, it means you're delaying it. And I mean, I don't know, doesn't it, maybe this is just my problem, but don't you, when you see, if I showed you these two signals, doesn't it kind of look like this one is the delay of that one? Yeah, okay, well, it's not. If you actually think about what it means, this is the delayed version of that, and let me explain why. The reason is, for example, this guy has this big peak here. This guy has this big peak at a larger time. What does that mean? It means it happened later. Okay? So I'm still always confused by this, totally. I mean, and then in 101 it's totally confusing because people talk about phase lead and phase lag, and then you see one sinusoid, it's obviously moving to the right. Then someone says, yeah, now it's delayed. So anyway, that's the, if you're confused by this, I'm still confused by it. So I just sit down and take a deep breath and figure it out and go, okay, something's to the right, it happened later, it's delayed. So anyway, this is the version. Now, it turns out here, if you work out the Laplace transform, what happens is you integrate from 0 to infinity of this, by definition. This is 0 up to time capital T, that's the delay. And then you get e to the minus st f of t minus t. You change variables here, and you get this very important expression. Okay? It says that the Laplace transform of a delayed signal is the Laplace transform of the signal times e to the minus st. Okay? And so that's, again, something you'll be very, very familiar with before this class finishes, and you will use in many, many other courses, I promise. And it says that delays in the time domain correspond to multiplication by e to the minus st in the frequency domain. So that's the idea. And then armed, you need to know this for two reasons. First of all, if you have to calculate the Laplace transform of something with a delay, but also you need to know it because if you're working out the inverse Laplace transform, the way humans do and not the way the formula tells you, you'll need to recognize when you see terms like e to the minus st, there will be a neural connection made from there directly to the word delay. So you will see, not yet, but within weeks and certainly after this course, from now on, e to the minus st, well, s, by the way, from now on will mean differentiation to you. 1 over s will mean integration. E to the minus st will be delay. And that's to the point where people don't even say it. And I mean, they just talk. This is the language they speak. So, but you're just learning it now. So this is the first introduction. Okay, so you know what time it is? I think it's quiz time. So I guess we'll go 10 minutes and then quit.